Chapter 9, we're going to talk about the effective reproduction number and the exponential growth rate E. RE is the effective reproduction number. In this country, it's RT. Britain, it's RE, but we're calling it RE. We'll go with that. T is the average number of days a person is infectious. And D is going to be the number of infections per day. So, for instance, if the effective reproduction number was 10, that means each person would infect 10 individuals. And if you're infectious for 5 days, well, D would be 2 infections per day. Times 5 days is 10 total infections. That's what these variables mean. You'll recall before that R sub E was natural log of D plus 1. If you have the daily infection rate, you can go to the exponential infection rate using this natural log formula. D is actually equal to RE over T, like we saw before. 10 over 5 would be 2. And so you can just make a substitution. And you can define RE in terms of these epidemiological variables. These are epidemiological variables that are talked about quite a bit, the effective reproduction number and the infectious period. So, and of course, if the number of initial infections is 2 magnitudes less than K, the total number of susceptible individuals, then we can use RE as an approximation for R logistic, or RL. So we're just going to back it up a bit and solve an interesting problem. Suppose we have RE equals 2.0, and we have an infectious period of 7 days. That means an infected individual would infect on the average 2/7 of a person per day, times 7 days is 2 people. We have an initial infected population of 25, total susceptible population of 10,000. Let's set up both the exponential and the logistic model. Well, first of all, we're going to use our formula right here. RE is equal to natural log of RE is equal to 2.0 divided by 7 plus 1. Okay, tau goes in the denominator. That's a tau. And then plus 1. Then we want to take the natural log. And let's see what we get. Okay, we hit the natural log. And looks like we get 0.2513. Now we have I0 is equal to 25. So now it's very easy to plug into this model. I of t equals I0, which is equal to 25, e to the 0.2513t. And there's our exponential model, which we know works fairly well in the early stages of the disease, but eventually it goes totally off the rails and diverges from reality. So now we want to set up our logistic model. The exponential model, just to review, gives us an exponential curve, and this logistic model gives us an S-curve. So this is an improvement. These basic parameters, we can state them, of course. That's 25. K is equal to 10,000. And we're going to use RL equals, drop one significant figure, 0.251. Those are all the basic parameters we need. Now, if you just want to do a check, what's 1% of this? 1% of 10,000 is 100. Okay, just move the decimal over 2 places, and 100 is definitely greater than 25. Okay, so this is less than 1% of that, so it's definitely we're able to make that assessment here. So now our model is I of t is equal to, K goes on top, 10,000 divided by 1 plus 10,000 minus 25 divided by 25 e to the negative 0.251 t. And there's our logistic model. Of course, I'll leave it to you. You can subtract 25, divide by that, write this as one numerical coefficient. That gives us the logistic model. So we're able to formulate these two models in terms of these two important epidemiological variables. These are important for study of the spread of any infectious disease. That's chapter 9. We're skipping chapter 10. I included chapter 10 in the problem set. You're welcome to read it. But this late date, we have a lot of trig to cover, so I thought I'd forego that. Chapter 11, we will go over the SIR model. And the problem with the logistic model is that assumes once infected, always infected. And that's actually not true. If you have an infectious period of 7 days, then whatever the infected population is, 1/7 of them become recovered. And that happens on a continual basis. And so the infected population, constantly people get siphoned off. And so, of course, that affects the spread of the disease. You have the susceptible times the infected, but the infected is much less than we have in the logistic model. We correct for that. The SIR model, pretty important. I have a very clear, simple exposition of that that we'll pass out next time, and you'll be able to understand what the epidemiologists are talking about when they mention the spread of the disease. So that's all for this video. I think that should be enough to do the problem sets. It's pretty straightforward. So.